Hi everyone. We're happy to have you this afternoon, this morning for me. We're happy that you joined for the Bioptim session. Today we are going to see the Bioptim software, which is a biomechanical optimization control software that we are programming at the S2M lab. I'm Benjamin. I'm a PhD candidate at the lab, and I'm the lead programmer on Bioptim, but also on other projects such as BioRBD and EasyC3D. I'm with François. Maybe you can introduce yourself.
Yeah, sure. Thanks, Benjamin. So I'm François Bailly. I'm a postdoc at the same lab with Benjamin, and I'm also working on Bioptim and the software suite from the lab. And anytime soon, we are going to begin this workshop. Maybe we can just wait a few more seconds for people to join.
Yeah, of course. And we invite you to go to the web link that I just posted here and that François did post in Wova, so you can have a try at the same time of us.
So welcome to the Bioptim workshop. I would like to begin this session with a really quick introduction to trajectory optimization. Indeed, as you may know, Bioptim is an optimal control software, and optimal control is a tool to solve trajectory optimization problems. I will keep it quick and general, just to give you a taste of what is behind Bioptim. So first, why talking about trajectory optimization in biomechanics? I could have started this presentation with historical trajectory optimization problems, such as the brachistochrone, rocket control, etc. But I figured that the audience today is mainly composed of biomechanists, so I decided to directly dive into the applications that we really care about. So there are mainly two families of problems that are crucial in biomechanics and that belong to trajectory optimization problems. The first family is the one of motion prediction. So for anyone who has already worked with musculoskeletal models, I'm pretty sure you have encountered such a situation in which you ask yourself, could I find a trajectory of control inputs that the system perform a desired task? And then you add, I forgot to mention that there are a bunch of constraints that I must respect, kinematic ones, collision-free, etc. And by the way, it would be nice to minimize an objective. For instance, energy expenditure, the time to perform the task, etc. So this is a typical trajectory optimization problem. And for instance, you might want to ask your computer, please find the muscle activation that make this model run, and while minimizing energy expenditure. And you'd expect to obtain something like this animation in return. Yes, something like that. So the second family is the one of motion tracking problem. Even if the application is quite different, their formulation is really close to the previous one. There is just one additional input data to the problem, which is the notion of measurements. So the statement becomes, given a musculoskeletal model and measurements, find a trajectory of control inputs that have driven the system around these measurements, subject to constraints and while minimizing an objective. In other words, you want to find a dynamically consistent state trajectory for your model that will mimic some experimental recorded motion. So the reason why both families of problems belong to trajectory optimization is that we can mathematically formulate the problem in a generic way, which looks like this. It's a minimization problem. So using X, the state, and U, the control, as optimization variables, you want to minimize a function, so this function, over a certain time horizon, big T, which is the duration of your motion. And the whole thing is subject to a bunch of constraints. So let's go together through the constraint set. First and foremost, you want your optimization variables X and U to be dynamically consistent. That is for all time T. You want this ordinary differential equation to be true. It's the dynamics of the model. And then the optimized control should belong to a set of admissible controls. Same goes for the states. And you might want to add initial state constraints. So that looks pretty easy. But the problem is that it's not so much easy to solve. As you may know, depending on your application, the objective function may be highly nonlinear, or the whole problem might be non-convex, plus X, so the state variable might be pretty large. So this leaves us with a time continuous, large, nonlinear optimization problem. So how are we going to solve this? So I lied to you before, because in the introduction, I told you that I would only speak about biomechanics. And now, after talking about mathematics, here is a cannon shooting situation. Sorry for that. I took this example from the blog of Matthew Kelly because it is a simple one, and I believe it's really illustrative. So the aim of this problem is to shoot a cannon to reach a target. If you look closely, you will find all the ingredients of the previous slide, including the cost function to be minimized, the ordinary differential equation, so here, that are constraining the problem, and the boundary condition on the state here. The first intuitive way to solve this problem is to use what is called single shooting, a single shooting approach. So single shooting works by approximating the trajectory using a single simulation. In other words, you fire the cannon, you check where the ball landed, and adjust the initial speed and repeat. In math terms, the error between the target and where the ball landed is called a defect. And the optimization algorithm will try to find the initial speed such that this defect is driven to zero. It turns out that single shooting is an effective method for simple problems like this one, but it will fail on problems that are more difficult, such as the one we are interested in. So one of the things that are implemented in Bioptim is multiple shooting alongside direct collocation. So I'm just going to talk about multiple shooting here because it's very similar to single shooting, but it turns out to be much more robust on difficult problems. It works by breaking the original problem into many small single shooting problems and then solving them in parallel. That is why we generally refer to it as first discretize, then optimize. Each segment begins with what is called a shooting node, and at each shooting node, the state and the control are optimization variables. At the end, each segment is constrained to connect to the previous one in order to respect the dynamics of the model. So to sum things up, in multiple shooting, the problem is bigger, but easier to solve. To conclude this presentation, I would like to warn you about common pitfalls of gradient-based optimization. Indeed, all the solvers that we will use to solve our multiple shooting problems in Bioptim are gradient-based solvers, so either IPOpt or Akados at the time. This means that they try to minimize the objective function by choosing descent directions based on local derivative information. As a consequence, the solver might end up in a minimum, which is not the global minimum, and then you will get a suboptimal solution to your problem. Another consequence is that you have no guarantee that the solver will converge, and therefore you might spend some time waiting in front of your computer, waiting for things to wrap up. So that's it for now. Thank you for your attention, and if you have any question, I'll be happy to.
All right, thanks, Francois. I'll step in. So now we're going to talk about how to actually solve this problem using numerical approaches. And we have developed Bioptim, which is a software to solve to prepare the problem to be solved. So it, as Francois said, it's going to be solved in IPOpt or Akados, but it has to be prepared some way, and Bioptim is going to do that for you. So in biomechanics, most of the things are done in skin marker, using skin markers, inertial measurement unit, electromyography, all these measurement unit that can be used to try to capture the movement from someone. The usual flow would be to the inverse flow. So we start with the kinematics and we go backward up to what caused the problem. So in this case, it's mostly muscle activation, but it could be brain activation. It's not really important where we stop in the inverse flow. The main thing is going from the measurement, it feels natural to go that way. Unfortunately, it depends highly on numerical derivative. There are usually residual, so it's dynamically sorry, not sound or inconsistent. And obviously there are sometimes multiple causes that can create one kinematics. So we have to use optimization backward, and we have to know the criteria that are minimized in order to find which cause is the right one, which is hard to do. And it does not easily allow us to investigate these causes. So we want to go to the direct flow as explained by Francois earlier. So we want to start from the muscle pattern and go to the kinematics. So the pros is you can test for a different set of causes because you starts with them, so you can enforce them in some way. By definition, the dynamics of your system is going to be sound, and it more focus on the goal of the task and not on actual kinematics that is uh, measured. It can be, but it can be completely in silico data. The cons is mostly that it is highly time consuming, so it's really hard to formulate these problems, so it doesn't take hours to solve. I'm gonna skip this part because we already talked about that. And so Bioptim is a minimalistic way to writing optimal control program in a few lines of code. That's what we're going to see in the next 45 minutes. It is intuitive as it's based on Python for the user end interface. And it is highly effective thanks to BioBD, which is based on RBDL, which is an implementation of the Roy-Featherstone's equation. So why BioRBD and Bioptim? Bio stands for biomechanics, so applied physics on biological system, and RBD for rigid body dynamics, so skeletal and musculoskeletal modeling, joint interaction, environment interaction, anything that you can think about of a software that uses rigid body dynamic systems. High level and low level programming. So high level refers to Python and low level refers to C++. Bioptim is based on the state of the art. So it's based, as I said, in RBDL using the space geometry of Roy-Featherstone. So it's efficient and most important, it is written in C++. It's used in robotics. So we can say that it is a quality, and we augmented it using Casadi. So right now, RBDL is available using Casadi, but it's thanks from the implementation that we did at the lab. It uses algorithmic. It creates algorithmic differentiation of the code. So it's really highly effective to get the derivative of any function. As I said, it is all written in C++, so it goes as fast as it can. And we are using state-of-the-art software to solve, so IPOpt for robustness and Akados for speed. But in the user backend, so anything that you are going to interact with is done in Python. So you can modify Bioptim only from the Python side. So you want to create a new constraint function, new objective function, and new anything that can be done only in Python. So if you're not fluent in C++, that's the way to go. To install it, it is very easy as it is a package from Conda. So if you're using Anaconda, you can install it basically using this one-liner over there, Conda install Bioptim, from the Conda Forge channel. And it's available for Windows, Linux, and Mac. Here are some examples that you can optimize using Bioptim. So targeting a specific point in space using muscles and muscle-driven optimal control. You can do a jump, so a mixture of dynamics. So there's the dynamics on the floor, there's the dynamics in the air, and also optimizing cyclic movement that can be done also. So today we are going to explore Bioptim together. So the example that we're going to implement together is the inverted pendulum. So the goal is, as demonstrated here, is to try to make the pendulum upward by moving only leftward or rightward the little cart over there. So it's a 2 degree of freedom. There you go. So the goal is to have it inverted, but as you can see here, it takes a very long time to be able to get it upward. So the goal is to find the best way to move the cart so it lifts the pendulum upward. Yeah. So let's go. Let's dive into it already.
So in this binder, you can see that there are a lot of examples. We won't have the time to go through all of them today because we only have 1 hour. So as Benjamin said, we are going to make just a simple example of an inverted pendulum. But if you are interested in going in the other ones, don't hesitate, and we can give you some feedback afterwards if you have questions, if something is unclear or anything. So in the meantime, I can comment the first lines of code. So okay. Sure. So as you can see, once you've installed Bioptim with Conda, so here with this interface, Bioptim is already installed in the Jupyter. You have nothing to install on your computer. But if you install the Bioptim package on your computer, you just have to import both libraries. So BioABD Kasadi, on which Bioptim depends, and then Bioptim, and you're ready to go for a small example as the one we are going to do today.
All right, thanks, Francois. I can step in again right now. Here is a simple example. Please note that these examples will stay pretty much forever. You can always access them via GitHub. So if you want to have a try in the next month or so, you're going to be able to do this without any problem. So we have prepared here the full example of what I've shown just prior. So the pendulum, the inverted pendulum, and we're going to go line by line. I can increase the size of it. We're going to go line by line. So you're going to see how compact it is to write the full problem. So as he said, you have to import. This is a very classical thing to do in Python. Here we are going to use a pendulum model, so I can show you very quickly what it looks. It's a very small file where you have the translations defined, the actual range the pendulum can go, his inertia values, and we added some marker just to show things a bit cleaner. So we load this using the BioRBD model load model function. And from that point on, model we're going to be able to get some information from the model. So for instance, here we have the number of degrees of freedom, so NBQ, and we just store it so we can use it later. Final time is the time that it's starts from the down and go to up. So we leave it exactly 1 second. This is not a problem where it tries to do it as fast as possible. It could be. There are ways to do that in Bioptim, but right now we wanted to do it in exactly 1 second. And for the end shoot, this refers to the shooting problem. So if you have a multiple shooting problem of 30 shooting points, then you would write the end shoot to 30 points. The dynamics here, we are using a torque driven, so it's a generalized forces thing. So the way the model is driven is it can apply force on the directly on the model. So leftward force to accelerate it on the left, and right force accelerate it on the right. And we're going to see later that the actual rotation, it's impossible for the model to drive it. So the easiest way to go from down to up would be obviously to use some kind of motor that rotates from the downward position to the upward position, but we prevent the model to do that. Here are the states bounds. So the states bounds are given, they can be directly extracted from the model using the q and q.bounds. So as I said earlier, there are ranges here. So the range refers to the -1 to 5 refers to the translation here. -2 pi to 2 pi refers to the rotation. So so when you're using q and q.bounds and you provide in the model, it automatically finds the state's position for you and fill everything. You may want to change few particular things. So in this case, we decided that we wanted the initial position to be 0. and we wanted to the final position to be 0, 2. So for those who are not familiar with Python, this means all the values. So all the values refers to the translation, the rotation, but also the translation velocity and the rotation velocity. So all of these at the very beginning point and the very end point must be equal to 0. And on the second line, we're just changing one of them again. We are changing the rotation. Final position must be pi. So we want to start, everything starts with no speed downward at the position 0, and it ends with no speed upward with no translation. So this is what these 3 lines are for. Then we have the control bounds. For the control bounds, we are defining minus 100 newtons for the translation to 100 newtons, and again minus 100 to 100 newton meters for the rotation. But again, here for the rotation, we actually set it to 0. So another way that we could have written it is like that. That would have been the same, and without this line over here. So that would be minus 100 to plus 100 for the translation, but we constrain the rotation to be 0. So it's not able to use this virtual motor to rotate. I'll just leave it like that, just make sure I don't screw things. And then we have to provide some kind of objective. It is possible to not provide any objective. It will try to optimize it. Obviously, if there is no objective, then as soon as the constraints are respected, it's going to be happy. In our case, we want to do it with the minimal joint torque. So we have to provide the key tau that refers to the tau control, which is the generalized forces. And you could use a lot of different objective. It could be minimize control, minimize states. I can show you later if you want to what kind of objective you can go to. Afterward, you have to define some initial guesses. So that would be what you think is the best way to start. If you don't know what to do, the go-to value is just to put zeros. So that's what we're doing here.
In practice, the initial guess part is a really important part of optimization, nonlinear optimization, especially in trajectory optimization. But the thing is that this problem is a small one and a pretty simple one. So we can be dumb and just give it as a nasty initial guess that won't help him at all, and he will find a solution, as you will see.
Yeah, and obviously, the more you have something complicated, the more you want to have something precise. But please note that IPOpt is pretty good at finding itself at some initial guess. So even though you don't provide a good one, IPOpt may find a solution anyway. But that won't be the case for Akados. Akados needs to have a good initial guess. So one way to go to find a good initial guess for Akados could be to solve the problem once with IPOpt first. Then you create the full program using the optimal control program method. So you send it everything that we just seen before. So the model, the dynamics that you chose, the number of shooting points, the final time to do the thing, initial guesses, bounds, and objective function. If you had some constraint, you would add them over there too. And this returns you one instance of the optimal control class. So I'll just run it. And then from this optimal control class, you basically just have to run it. So you can run the solve, and it launches by default IPOpt. So IPOpt solves the problem by itself and it's going to be happy. If you see optimal solution found, you can smile because it means that you have actually found a solution, which is always a very good start when you are solving these kind of problem. Obviously, we designed this problem to work. So if you don't see that, that's an actual problem. And finally, it returns you a solution. I'll just go back here. The solve method will return you a solution class, an instance of class, and you can use other values to other method with this solution. So one of them is to print. So it's going to print you some values. For instance, the solving time. It's going to print you the cost function that you are trying to solve. So if you have multiple cost function, then they will be separated over there, and the constraint as well. And finally, you can graph them. Please note that automatically organize refers to have them in the screen separated, but obviously on the binder it doesn't work, so it has to be false. Usually, you would not write anything over there, and it would just neatly place the graphs for you. So here's are the graph that you get from this program. So the top row here is the degrees of freedom. So you have the translation got by the system, you have the rotation got by the system. The second rows is the velocity, and the third row is the generalized forces, as it was the controls. As you can see, the controls are in the different color than the I would say the states, but this is not that gives the answer. So the reason is these are integrated values, and this one, since are the control, are just normal values. And you can see that this is step function. If you want, you can change the step function for continuous function, so they would be lines instead of step function. But for most of the program, you would want to use the step function, as they are easier to solve for the program. And as expected, there is no general forces on the tau. So now I can actually show you the thing. The binder doesn't allow us to use the animation. So I'll just swap to my own computer right now in here, and I'll start the same program, but the only change was here. So instead of using a graph to actually show the graph, I'm animating it. So you're going to see at the screen some animation from it. And also in the solve, I added this show online optim. So if you add these values over there, it will during the optimization, it will update the graph. So obviously today it's going to be too fast because Pendulum is way too easy to solve. But in long program, you see each step of IP up. So if you have some problem with your optimal control program, you can use this show online optim to try to find which time frame has problem solving. So I'm going to solve the problem. So again, that was way too fast to see anything. But here's the important bit. It is the pendulum. So it's a different shape, but the same idea. So here you have your pendulum. I'll slowly move forward. So it gives a push to the our right, seeing in the front, but it's on the left for it because we're seeing it from the face. And then it push on the left, and it uses the inertia of the head to lift itself and finish directly upward. So this gives obviously exactly what you wanted to do. Using this button over here, you can actually save the video in the OGV format. So you just press it, you go where you want to save it. So let's call it Pendulum. Save it, and you just press play, and then it saves every frame. If you want, for some reason, to record multiple frame of a single position, you can press the plus button here repeatedly, and then you can press play, and it automatically stop when it reaches the end of the time. And when you're done with your video, just press the stop button here, and then it's recorded on the computer and can be shared to everyone in the world.
So I just want to mention that this solution is more elegant than the one that Benjamin showed you during his presentation.
Yeah. So it wasn't like that, and at some point it tries to find to go upward, obviously. So, are there any question yet about show online does not work in Windows yet? Yeah, that's right. Thanks, Mikael. If you want to use the show online, it currently has to be in the Unix system. It's because of the way pickle works. So this is going to be a hard problem to solve. But if someone is interested in solving this problem, we're going to be happy to support the show online Optim for Windows soon. So if there's no more question, no other question about this actual program, we can move on to another program. Are you happy with this one, Francois, or you wanted to show another one?
No, it's okay for me.
So I can continue. I'm going to go fast on this one because it's mainly the same. So it was designed to be an exercise, but obviously we won't have time to assist you with the debugging and everything. In a workshop formatting where we have 2 hours, we can actually let the attendees work on this program and work with them to solve it together. Um, what I suggest you to do is that if you found Bioptim interesting and you want to have a try, I really suggest you that you go with this one and try to fill the blanks. So every dotted here is something to fill, and we provided the solution as well. So I'll just open the solution for today, but that is a very good start to go with the exercises. So again, you want to import everything. For those who are familiar with Python, they could be very afraid that you're seeing the star here. Usually we never use it, but it's just we didn't want to this import to be very big in these examples. So we are using the star here, but please know that we know it is not good practice to do that. So again, we're defining the final time. So the what we're trying to do right now. So let's just read this the OCP that we are trying to solve. Movement. Oh, and that's an artifact from the past. Movement of 1 second divided in 50 shooting points. The states again are the position and the velocity. The control this time though will be the muscle activation. So instead of using some kind of a magical motor that drives the joint, now it's going to be actual muscle activation. The cost function is to minimize the control, so minimize the muscle activation at all time, and minimize the Euclidean distance between two markers at the final node. So we start at a certain position, and the goal is to lift the arm to a certain point, and we're going to minimize the distance between these 2 points. So one point is at the end, and the other point is floating in the air. Initial guess are arbitrarily set to zero 0.5 for all the muscle activation and 0 for anything else. So again, this is a very easy problem to solve. So we can be very sloppy with how we are defining the initial guesses. So final time 0.5 seconds. We wrote 3, but it's a 0.5, and end shooting is 30. So these are better values. We just changed the model recently and just found that these value works better for this program. The model will be the ARM26. So if you are familiar with OpenSim, this is a BioRBD implementation of the ARM26 from OpenSim. The different values that we're going to use is the number of generalized coordinates, number of generalized velocities, number of generalized forces, and a number of muscles. So we're just saving these values for later use. Now that we're having multiple objectives, we have to define an objective list. So if we didn't, we could just write objective like that. But since we're using an objective, multiple objective, it has to be stored in a list. So we're defining this list over there, and we can use the add function to define new objective. The way we have done them is if you only have one, you can actually just type the thing exactly like that. So there's no difference between the add function and the constructor from a single objective. We are using a Lagrange objective because we want to minimize the generalized forces and the muscles across all time. You can add weight. So the weight would be how more important or less important a specific objective function is in comparison to the others. And finally, we have a Meyer function too, which is for this case a superimposed marker. So you have the first marker, which is the target, and the second marker, which is the COM. Sorry, I'll just move to the right. COM hand, which is the center of mass from the hand. So these markers are defined in the biomod. I won't show you the biomod, but it is basically the same as the pendulum we've seen earlier, but with these marker defined. The dynamic that we're using this time, we're using muscle driven. Muscle driven would use the muscle to compute the generalized forces from the muscle, and at that point, it takes the generalized forces and convert them to generalized acceleration, and then integrate twice. For some reason, you may want to add not external, residual torques. So, for instance, if you think that your model may be too weak, you may want to add them. These are the exact same dynamics I've shown before. So it creates some kind of magical motor at each degrees of freedom and drives them. But obviously, if you're interested in muscle driven, you want to be them to be as low as possible. So that's why you want to have these objective function here that minimizes the generalized torques. After that, again, you have to define the bounds. So you are defining the Q and Q dot bounds. This is another way to define the same thing as before. So before we were using not a list. Here, the list is not mandatory because you only have one phase. But if you're using more than one phase, you will have to define a list, and each add will add a specific phase. You can add them in different order by specifying the actual phase that you want to add. In this case, again, there's only one phase, so it's not mandatory. But we wanted to show you that it was possible to do that. If you do, you will have this to specify the phase when you want to change something. So in here, we are changing the first node, all the states to 0.7, 1.400. So 0.7 would be the first degree of freedom. This is a 2 degree of freedom model. So the first is the rotation of the humerus, and the second is the rotation of the arm. And this position corresponds to approximately this, so having the arm at 90 degrees from the ground. Or parallel to the ground, sorry. Initial guess, we are just providing some initial guess, pretty much random values. Again, we're doing some defining some path constraints for the control. The minimum value for the control will be 0, the maximum value will be 1, and the initial guess will be just arbitrarily set to half of them. And we are defining also these residual value that I talked before. So we're defining them to minus 5 Newton meter to plus 5 Newton meter. And then we just add this minus value and then this plus value over there. And finally, we just provide one initial guess. So very, very similar to the previous one. Then we are constructing this new instance of optimal control program. So let's just run this, and then you can solve the problem using the solve function. So now this will be solved by IP-up. You see that it's going to take a bit longer. Again, this is because of binder, so I can simultaneously solve it in here. Run. So as you can see here, you're seeing the updates that I was talking before. So each iteration, you see the IP up trying a new solution. At the very beginning, you may have seen that it was discontinuous. It's because IP up did not find a good solution yet, and now it's done. So you have the animation. I'll come back to animation just a bit later. So is it done? Not yet. So that's what I meant by it is much slower. It's you've seen that I could actually solve the full program running it after starting it after. It's just because this one uses only one thread, and on my own computer I can actually use more thread. And then okay, let's just print some graphics. Again, this would be the exact same as this one. The same graph actually. We can print the solution. So here again, you can see that you have different function that can be shown. So IPUp will give you some values, some n values for your objective function written in here. And if you want to know which value correspond to what, you can decompose them in here. And just as a final thing, this is a bit complicated. It's because of the Casati way of doing thing. But I just wanted to show you how you could manually compute the distance between the two marker at the end, and the distance is 30 millimeters at the end. And if we want to see the actual movement, so I'll put it on the left like that. So it starts by just using the gravity to pull the arm, and pulling the arm a bit actively too, and then actively raising things. So that's the minimal way to bring everything to bring the arm at a certain position. So the final position is this one. The markers that it tries to target is the marker over there. I'll just make it a bit centered. The marker over there, and it tries to bring the hand to it. So you see that there's a certain distance, and the reason there's a certain distance, the first one is it's a 2D model, and the tracking part is not in the path. So it will try to find a minimal distance, but it is impossible to have a perfect one. But you see that the best way would have been to be here, and and it is not. Sorry about that. It is not, and the main reason for that is because you have a competing objective function. So the one of the objective function is to minimize the joint torque. The other one is to minimize the muscle activation, and another one is to minimize the distance between those two. So if you want to increase the value of this objective function, so the importance of this objective function, you would have to increase the value of the weight associated with this objective function. And that's pretty much it. I do have two other examples, but I suggest that we are taking questions if there are any. The two remaining example is a multi-phase one. So the multi-phase is when you change the dynamics of the system. For this example, we have a jumper. It has one. It has a phase where there's a contact on the ground, and there's a phase which is a free fall phase, and we show how to start from one to the other. So we have a multi-stage, multi-phase optimal control program. This won't work in Akados, though. Akados necessitate a single phase program. And finally, we have an MHE, so moving horizon estimator example, where we have a large horizon to solve, but we are doing it a very small section at a time, and we just using a moving horizon, a moving sliding window. We are going towards the end of the program. So this could be used, for instance, in real-time application of any program. Do you have anything to add, Francois, or you're still hearing yourself in an annoying way?
I think I fixed the problem. Yeah.
Good.
Can you hear me? Okay.
I still can hear you.
At the time being, I'm seeing no question, whether in Ruva or in twice. Okay, so Dieter asked, is it possible to export the dynamics?
Okay, but I'll try to answer the question. I'm not sure what you mean by exporting. Oh, as a C code. No. But yes and no actually, because the dynamics of the system is written into RBDL for most of the thing, but no, there's no exporting feature. So if you wanted, for instance, to define your own dynamics, which is possible in Bioptim, you would define it into Python. That said, it is Casadi variables. So even though if it is not in C++ or C, it is very fast because of the way we're using the Casadi variable. So it doesn't matter that it is in Python.
And please mention Akados, Benjamin, because you can export C code in Akados.
Yeah, of course. Yeah, you're right. If you're using a Kados, but again, there are some limitation. For instance, you can't have a multi-stage program. A Kados, by definition, if you start the program, will do an export C code by default. Actually, it's mandatory. So it will indeed export the C code for that. Thanks for slapping my hand. Of the OCP, yeah, the full OCP, obviously, but I think it's just the dynamics that is exported in not the full OCP. It's just the important bits that are exported. How the hands try to move to the target. So you mean, I'm not sure what you mean by how. The goal, what the software what IPUp tries to do is try to find the path to move the hand from down to up, and it uses the muscle to do so. So it will try to find muscle activation pattern that when you apply it to the system, it creates the movement wanted. So what it means, and because the tolerance that we're using are so low, you can at the end take the control time control solution, and you can take the only starting position of your system, and you can apply some kind of single shooting simulation, and you should find the same thing as the optimal control program found you. So if you don't, that usually means that you didn't use enough shooting points, or if you were, for instance, in direct collocation, because we're supporting direct collocation as well, you may want to increase the polygon that you're using. If you are in the multiple shooting, you may want to increase the number of shoots, or increase the number of steps between the shoots. There is Runge 4, which is implemented, and also the Runge 8. But most of the time, if you have something that converges, you can do a single shooting, and you'll find the exact same answer. Are there any question left?
You can mention the graph, Benjamin, PDF.
The graph? What do you mean?
The PDF graph.
Oh, yeah. Some new features that appear recently is the capability of the. Okay, so that's always dangerous, but I'll try to add them right now. So I'll just remove this part. If you for some reason want to have a nice look at the optimal control program that you are solving, you may want to produce the graph of it. So that definitely helps to see if you've made any mistake in defining your program. So if you print it in a PDF like that, you get this. So you get the model that you're using, the phase and the nodes, the what kind of dynamics is used for this particular phase, what kind of ODE solver. So in this case, it was the Hungekuta 4, and what kind of control type. So the step function for or the constant. If you have some parameters, you can define parameters that are across the optimal control phases. So you can 1 minute left. Thanks. You could do, yeah, as Michael mentioned, parameter identification. What are the Lagrange objective function? What are the Myers objective function? And what are the constraints of the program? So it can get very big. I'll try to do the same with the ARM. Yeah, works first try. So in this case, you have, for instance, the model, and again, every information, the Meyer values are there, and it tells you where they applied. Meyer function traditionally are only apply on the end point, but you can change it for any points you want in the optimal control. And yeah, every information that are needed can be seen over there. So that's a really neat way to visualize if you made any mistakes when you constructed your program. Thanks everybody for attending, and sorry for the sound problem. Yeah, so sorry too that you could not step in because of the sound. I can stop the sharing. So I think you're still muted. So thanks everyone for attending. I hope you enjoyed the introduction to Bioptim. I hope you're gonna give it a try. As I said, if you want to install it, it's pretty easy because you just have to install Anaconda and install it from Conda Forge. If you want to install it by hand, you can go on the README, and like that you can follow the latest release, because obviously there are still development on this. Yeah, thanks for attending. I wish you a very good end of the conference, and it was a pleasure to be with you today.
Pleasure shared.